Welcome to Calculus 1, Section 8. We'll start with Section 2.1 from the book. We'll be following the book very closely. So in this particular video, we'll try to cover the concepts of average velocity, which will lead to the concept of instantaneous velocity. Then we'll proceed to study a geometric version of this. Namely, we'll study the slope of the secant line to a graph on a particular point, which then, with the same process that allowed us to define instantaneous velocity, we'll get the slope of a tangent line. Okay, so these are the main concepts of this section. Okay, so the main notion here behind all of this is the notion of limit. So let's consider a function f defined over an interval ab. So what's a limit? A limit describes how the values of f behave as x gets closer and closer to a given number c inside the interval ab. And so if f of x approaches a number L as we get closer to the number C, we will say that the limit of f as x approaches C is L. If there is no such number, where L, meaning that f of x doesn't get closer and closer to some real number, L, then we'll say that the limit does not exist. Okay, so some small examples. Of course, we will go over more detailed ones as we get more into the actual definitions of things, but just to get an idea, we'll have two graphs, two functions f, function f of x. This is a value c sitting inside some interval ab, and here we see that as x approaches value c from either side of c, the values of f get closer and closer to this number L over here. And this is what we'll write usually. So we'll write in this case that the limit of f of x as x approaches c is equal to L, or that f of x tends to L, or goes to L as x goes to c, or x goes to c. Okay, so in this case f is approaching a certain number L as x approaches c. As we will see later when we define this more rigorously, f need not be defined at the point c itself. We just need to know what happens as we get closer, but when we're not at the point c. Sometimes the function f cannot be defined at the point. Now, second example. Again, our point c, sitting inside an interval ab, and our function f of x. Here we have a value L, which is the value of f at the point c. We have another value down here, which is L1, we'll call L1, and we have yet another value L2 over here. In this situation, we see that if we approach c from the left, f of x is approaching L1 as x approaches c from the left. Similarly, we can see that f of x approaches L2 as x approaches c from the right. So as we move in this direction here, the values of f are getting closer and closer to this value L2. And the problem here is that L2 and L1 are not the same number. So f of x is not approaching just one single number, L, as f approaches c. In fact, f at the point c is defined in here and is equal to the number L, which is neither L1 nor L2. So in this case, the limit of f of x as x approaches c does not exist. Let's go over one final example, which is kind of worse than the last situation. So we have again our point c sitting inside some interval ab and a function f. In this scenario, we have a function f that possesses vertical asymptote at the point c. So in fact, if we were to say that f behaves in some way as f approaches c, we would have to say that as we approach x approaches c from the right, we see that f gets larger and takes on larger and larger values. In fact, it is unbounded, so it's natural to say that f of x goes to plus infinity. In the same way, if we look at this side of the graph, as x approaches c from the left, the only sensible thing to say is that f of x approaches minus infinity. So of course, if this is just notation for, the notation plus or minus infinity is just to mean that f of x becomes unbounded and is becoming more and more unbounded as you approach the point C. It becomes larger and larger after a certain point, or becomes very, very negative if we are approaching C from the left. So with these examples in mind, let's see why we care about this concept of limit. So let's consider the following questions. First one is, how do we define and compute instantaneous velocity? At a particular point in time. From high school or even middle school, we're used to computing the average velocity of a vehicle. We just divide how much has been traveled by the time it took the vehicle to go from point A to point B, and then we call that the average velocity. So how do we know exactly what velocity it's going at a certain point in time? So you cannot just divide 0 over 0 and expect to get a number. So we're going to try to make sense of what instantaneous velocity is. So in fact, we're after a definition of instantaneous velocity. In the same way, more geometrically, how do we define and compute the slope of the line tangent to a graph at a particular point? So we're already used to computing the slope of a given line, a straight line, and whenever we have a graph, we can compute the slope of a secant passing through 2 points on the given graph. But how can we even speak of a tangent line? And this is just a geometric version of what instantaneous velocity is. So we'll try to answer these two questions by using the notion of limit. So Furthermore, let's insist a little bit on instantaneous velocity. So what is this? I mean, what is this notion that we're after? So this should indicate, so we expect that it indicates the speed and direction of an object at a particular moment. If we consider an object traveling along a line, so that's the simplest situation that we may find, where we need to define velocity. Here there's only one direction. The average velocity over a given time is defined using the ratio. This is the all too familiar expression that we know from previous courses. The average velocity must correspond to the change in position, so how much has been traveled, all of that divided by the change in time. Okay, so this is formula that we all know, and for this we don't need calculus, of course. Thus, average velocity is the rate of change of position with respect to time over a particular interval. For example, this is a physical situation. If a car travels forward along a road or a highway 240 kilometers, and it takes him 3 hours to do so. 240 kilometers, more like a highway. 3 hours, then its average velocity is 240 kilometers, which is a change in position, divided by 3 hours, which would correspond to 80 kilometers per hour. We'll conclude this. I mean the velocity is just one instance of what we're trying to understand. So it's just one example of rate of change. It just so happens that it's very useful to understand the concept, because it has a physical interpretation. You can find more examples in the book. I'll point to those in the module. But so this is just the basic starting point of the course. So we just go over in the next video over some problems related to this section and more examples. So as you become very familiar with the notion of rate of change.